Okay, let's go over the sample test for Chapter 3. The price of a new car dropped from $15,999 to $13,500 as soon as it was driven out of the dealership. That's kind of typical. The prices of cars are a little bit higher now, but that's when I wrote this test, that was the numbers I used. Use this information to write one true statement using percentages as a fraction. So, a fraction. So I could take my calculator out and I could do, let's see if I can get this someplace where this shows up well. I could do 15999 divided by 13500 times 100 to get a percent. So I could say, so I divided by the new car price, or the price after it was driven off the lot. So I would say that the original price is 118.5% of, now in the fraction, the of is the denominator of, and I put in the denominator the current price, the price after driven off lot, of the current price, or the price after driving off the lot. So the original price was higher than that one, so it's 118.5. Now, if I had done the division the other way, so the other way to write the fraction is 13,500 divided by 15999 times 100, and I get 84%. Now, the important part on this, in writing this correctly, is getting the phrases right here. So now I'm dividing by the original price. So of the original price goes here. So the current price, the price driving off the lot, is 84.3.4% of the original price. So I could do either one of those, would be an acceptable answer using the percentage as a fraction. The original price was more, 100% of this price after the lot, and 18% more. Or vice versa, the price now is only a fraction of that. It's 84.4% of the original price. Okay? Now it says, write one true about the absolute change. Okay, so I can say so how much did the price change? Well, we're going to take 15999 minus, minus 13,500. And so the price, the value of the car dropped $2,499. That's the absolute change. The value dropped $2,499 when driven off the lot. Or I could say the original price was $2,499 more than the current price. Okay, so we're just showing the difference in the two prices and how they compare. This is called the absolute change, the difference in the two. This is a fraction thing. This is 118 out of 100. This is 84 out of 100, a fraction. Now it's a change. Okay, so now how much did the price change? Well, it changed by this and as a percentage. So we put the change, so I'll do it on the calculator first. So we want to do 2,499, and I could divide it by either one of these original prices. So I'm going to divide it by, let's do the first one, $15.99 times 100. So it actually went down that much from that price. And so it's going to be important to get the sentence right. This is what I'm going to be grading for, to get this right. The price dropped, dropped 15.6% from the, see, now I'm doing it. This is key. From what? From the original price. From because I'm comparing it to the original price. Now, I could compare the change, the $24.99, divided by the new price, the price after driving it off the lot, $13,500, times 100 to get percent. And I can see that the price of the car was 18.5% more. Now I could have said the price dropped, or the price is 15.6% less than the original price. This is the price of the car is 18.5%. The original price is it more than, so I'm being compared to the new price, the price after driving off the lot. Now I don't have to do both of these on each one of these. Just get one of these for each correct. So it makes a difference on which ones you put underneath, because that's the one you're comparing to. And that's important on the part A and part C. Part B, it's also important to, when you talk about then the original price or then the current price. The one you divide by, that's what you're comparing to. Okay, so that comes up again in this. The price of a lamp is $35.99 at the local store. So we got the local store, and the same lamp sells for $29 at Lamps Plus, a different store. So it's on sale at this supposedly big box Lamp Plus store. Write a comparison statement comparing the price between the two stores in percentage. Now you could do this kind of comparison, or you can do a fraction comparison, or you could do a change comparison. You got to do one of them. So I'll just do the fraction ones. And so if I divide these, put it up here where you can see it, 35.99 divided by 24.99. So which one am I comparing to? The one I divided by. So I'm comparing to the Lamp Plus. And so I'm figuring out the local store is, if I multiply this by 100, 144% more than Lamps Plus. The local store is 144% of, and now it comes to the one I divided by, the Lamps Plus. Now, if I had done the division the other way, 24.99 divided by 35.99 and multiplied by 100, I get 69%. And now I'm comparing it to the local store. And so the local store, I'm dividing by that. So the Lamps Plus, I have to end with this in my statement. So now it's local store goes here and Lamp Plus goes here. So I say the Lamps Plus price is 69% of the local store price. So it's key which one you put in the bottom. That's the one you're comparing to. What's Lamp Plus as compared to the local store? Or what's the local store compared to the Lamp Plus? Lamp Plus price was in the denominator on this one, and the local store price was in the denominator on this one. Okay, college-educated person earns 20% more than a high school diploma person's. So, college-educated person earns 20% more than a high school. High school diploma persons earn what percent of the college-educated person? So, we're comparing to the college-educated person. So we can say, let's just make a picture here. If this said the college-educated person is 20% more than the high school. So this is comparing to the high school. So if I say this is 100% of what a high school gets, then the college gets 20% more. It gets all of the high school. And if I divide this in 100 pieces, 20 of them would be about this much. I get 20 parts more. The college would get this much. So you could say if this gets $100, this gets $120. Get the idea? So the high school diploma person only earns what percent? So now we're comparing to the college. So I got to put in the denominator the college, the 120, and put the high school in the numerator because it says the high school person earns only what percent of what the college person gets. Well, the high school gets $100 if the college gets 120, 1,000 to 1,200, and so on. So let's figure out that percentage. 100 divided by 120 times 100 is 83%. 83.333, 83 and a third percent if you want to get a little bit more, or 83.3. Okay, minimum wage increased by 5%. The minimum wage is what percent of its previous value? Well, it's all of the previous value plus it increased by 5 plus 5% more. So it's 105% of its previous value. Shoes sold for 15% less than their market price. Marked price. The sale price is what percent of the marked price? Well, if they lost 15% of the marked price, 100% would be the total marked price. They lost 15%, so they sell at 85%. 15 off of the 100%. Ivan's credit card is 11% more than it was last. His debt is 11% more than last week. So it lost 11%, so it ends up being 89% of the current. Okay, let's say this right here. Whatever his card debt was, it's increased by 11%, so we'd take it times 1.11 to figure out the new debt. And they want us to say his debt was the old debt of its current debt. So percent of the current, so we got to go with the new. So we're going to divide by the new, which is this, compared to the old. So we got the old over the new, which is the old plus 1.11 times 1.11. So these cancel, and we get 1 over 111%. This one's a tricky one. So we get 1 divided by 1.11. 100% divided by what the new one is, 111%. 100% plus 11%, and that's 90%. This one is one that's often missed by students. Now, when I give this test, I'm going to mix these around so you just can't remember, oh, this is what I did on this one, this is what I did on this one. You have to know which one uses what technique. Okay? 2018, Americans drove 3.22 trillion miles. There was 226 million drivers. How many miles were driven? That should be driven, not driver, per driver in that month. In a month. So this is in 2018. This is for a year. So there were 200. Well, the number of drivers doesn't change much, but how many miles driven in a month will be a fraction of the total miles driven. Total miles driven is 3.22 trillion. That's times 10 to the 3 is 1,000, 6 is a million, 9 is a billion, 12 is a trillion miles. In a year, in the year 2018, I have to divide this by 12 to find out how much in a month in 2018. So I'm going to pull out my calculator, take care of that. 3.22 times 10 to the, that's double E, which is right there, to the 12, or you can write you could write that. See, that's this, or I could write 3.22 times 10 to the 12th. Same answer. That divided by 12. So that's how many miles were driven in a month. 2.6. And I have 3 digits here. 12 is exact. There are 12 months in a year, so that's exact. 12.000 months in a year. 2.68. I had 3 digits here, so I should do about 3 digits here, or maybe keep more and then in my final answer round to 3 digits. But anyway, times 10 to the 11th miles in a year divided by how many drivers, so I know how many miles driven by each driver. So I got to divide by 226 times 10 to the million. That's 10, not 3, which is 1,000, but 6 a million. So now I got to figure that out. I've got my answer in the numerator. I got to divide it by parenthesis. 226 times 10 to the 6. Or I could have wrote 226E6. And it comes out to be 1,187.315, but all this doesn't make sense. Miles per driver. So if I'm thinking about my significant digits, I should do just 3. So I should write about 1,190 miles per driver. That's what I should do for my answer if I'm thinking about the science and the significant digits and all that. Jeff Bezos, back in 2018, kind of around when I wrote this test, CEO of Amazon was estimated to be about $123 billion. If a stack of 10 $1 bills is 1 millimeter, so $10 makes 1 millimeter. And I want to know how high the stack would be for 123 billion $1 bills. Okay? So I got to take $10 and make it into 123. So how many $10 are there in 123 billion? Well, I'd have to divide this by 10, so I'm going to have 12.3 billion stacks of $10 bills, and each one is 1 millimeter. So each stack of 10. So I got 2.3 billion stacks of $10 of 10 $1 bills. That many stacks of them. And each one is 1 millimeter. So I got to take it times 1 millimeter. That many $10 for, I'm struggling to say this correctly. This many stacks of $10 bills. So this cancels this, and so I get 12.3 billion over 1 millimeter times how many millimeters are in a kilometer that we're supposed to go to. Well, there's per millimeter. So I got to get that out of there. So there are 1,000 millimeters make 1 kilometer, or make 1 meter. and then 1,000 meters, and I'm not doing this right. I'm not doing this right. Okay. I have 2.3 billion stacks of $10 bills. So there's this many a billion millimeters, because every 10 makes 1 millimeter. So I've got this many millimeters. In scientific notation, that's 12.3 times 10. 3 would be 1,000, 6 is a million, 9 is a billion millimeters worth of dollars. I got to convert this to kilometers, so I got to get millimeters to cancel. And there's 1,000 millimeters in 1 meter. And then there's 1,000 meters in a kilometer. So I've got to take this divided by 1,000 and divided by 1,000. So I got to take 2.3 times 10 to the 9th divided by 1,000, and then divided by 1,000. And so the money that Bezos has would go for 12,300 kilometers tall. That's how tall the stack of ones would be. Sorry for the confusion on that one. Now let's do 6. So how many significant figures in there? Well, if it's in scientific notation, the 2.8, there are 2 significant digits. The implied absolute error, it's half of the next place, so it's going to be 0.0, that's the 8, and half of that place would be 5 above that in the next place, or 5 below that, and that's in times 10 to the 5th. That's how much the implied error is. So the implied percentage error is the original the error divided by the original changed to percentage. So I've got to take the implied error, the 0.05 times 10 to the 5th divided by my original number, parentheses, 2.8 times 10 to the 5th, and I get this times 100 to change it to percent. So I have 1.8% error. 1.78, 2 digits, so I should probably do about 2 digits. So it's only 1 here, so, but anyway, that's close. Next one, there's 1, 2, 3 digits, because this is a 0 after the decimal, they count. So this one's measured, this one's measured, this one's rounded off on this place, so it's 0.005. 0.005 that it could be off by. So my percentage error is this divided by the original number. So 0.005 divided by 5.40 times 100, and I get 0.092593% error. This has more error than this. Now think about it. If I only have 2 significant digits here, that's going to have more error than if I have 3 significant digits. This has an implied error of about almost 0.1%, and this is almost 2%. Now let's take a look at this one. This is 3 digits. This is 3 significant digits also. So it's going to be close to this one. Which one's going to be better? So this one's going to be plus or minus. Oh, but this one doesn't have 3 significant because this is a 0 before a decimal, so you don't count it. It only has 2. It's 940, but it could have been as high as 945, which would round off to 940, or it could be as low as 935, which rounds off, so it's plus or minus 5. So this is not going to be as accurate as this one. This has 3 significant digits. This one only has 2. And so to get the percentage error, it's going to be 5 divided by 940 times 100 to make it percent, and it's got 0.53% error. This is almost 2% error. This is about 0.1% error. This is about 0.5% error. This has got the least error. This has got the most error. Okay, which is relevant to the next question. Which of the different parts in number 6 shows the least precision? The least precision is here. There's the most error, so it's got the least precision. The most, which of the following shows the most precision? The most precision has the least error, so that would be B, most precision, because it has least percent error. Or you could have said most significant digits. Either that or this. Now, which one has the least precision? Well, both of these have 2 significant digits, but the one that has the least precision, has the most error, is A, which has the most percent error. So if you can get these right, you can answer these questions pretty easily. Okay? Oop, I didn't have that where you could see it. Okay, I need to bring this back down here. Let me do this again. B has the most significant digits and the least error, so it's the most precise. A and C have the least number of significant digits, but of those, the one with the most error is A, and so A is the least precise because it has the most percent error. Okay, let's make sure this one's visible to you before I do it. It says, use the rules discussed in this chapter to get the right for the amount of the area of a rectangle. So we're going to multiply these. 75.3 times 10.452. Oh, what did I have wrong in there? Oh, I forgot to put times. 7.53 times 10.452. Got it in there now, right? Enter. I get 787.0356. But the rules in this chapter, what's our least significant number? This has 3 significant, this has 5, so I should give my answer to around 3. Well, there are 3, so I should be saying 787, and this is meters by meters, so meters squared. Now it says add. 7.2 plus 25.3059. Well, I get 32.5059, but I only have 2 significant digits there, so I should be going probably 2 significant digits. The 5 would round it off, so I should say 33, and I'm adding feet to feet, which is just feet. Not multiplying, so it's not feet squared. Okay, so now we got to find the volume of a box. Well, that means you're going to multiply length times width times height. So we're going to multiply these 3 numbers. So I'm going to go 9.2 times 140 times 38.1. And I get 49072.8 centimeters to the third. But these are not exact. This has only got 2 places of accuracy. This has 3. This has 3 digits, significant digits. So I should give my answer in the least number, which is 2. So the first 2 round the rest off. So 40, rounding to this place, this is 0, so I don't round it up. I just say to 49, put in zeros. 49,000 centimeters cubed. Each one of these has some error, and that makes it so these don't really mean anything. It could be bigger than that or less than that. Okay, and what we've been working on lately in class, it says, what if we have 2,000 people, (250 have cancer, so 20,000 people minus the 250 is 19,750. If I do my math right, subtract that from that, and I get that. Cancer test correctly diagnoses cancer. A positive test do have cancer. This is the correct box 94% of the time. So I got to take 0.94 times the number of people, and I get 0.94 times 250, and I get 235 people will test positive and do have cancer. That's correct results. That's approximately how many right. If there's 250 people and 235 are counted correctly, then by the percentages, 94%, that means here the rest, another 15 to make the 250, This plus this needs to add to be 250. So 250 minus that goes there. This is the test negative, but do have cancer. So this is a negative reading, so it's a false, it's an incorrect negative. It's called a false negative in the testing world. 15 people will get a test that says, nope, you don't have it, and they really do, statistically. All right, now don't have cancer. Well, the test should be negative, so this would be a correct test result reflecting the situation. And on that, the same test correctly predicts 90% of those that do not have cancer. So 90% of this number. So 1,9,700 times 0.9. It correctly predicts 17,730 people correctly. I did 1,9,750 times 90%, 0.9. So the rest of them, 10% of this goes up here, which is 1,975 people. I can do this times 0.1 or subtract this from there, and I get that number. I can add across. So this plus 15 would be 1,745 people that will test negative. And up here, I add these. That would be the rest. Or I can take this from this, which would be 2,255. That's what I should get if I added these two. And I don't. I did something wrong here. Oh, I know what I did wrong. I think. Let's see here. 19 times that is 1730. And I didn't do my subtraction right here. 90% goes here. 10% of this should have been this. Something's not right here. 1,97730. 1,9,750 minus 1,7,730 is 2,020. He gets 90% of this correct. Should have been 10%. Not sure. Oh, I see what I did wrong. I didn't do 90% of the right number to start with here. 1,9,750 times 0.9. Something wasn't working right here. This should be 1,775. And if I add these, I get 1,778. I didn't type this in correctly. And 10% would not be this. Be 10% of this is 1,975. These two should add to be whatever this from this is. Checking my math here. So 235, 35 would make a 2010, 2210, 2210. No, it should be 20, I think. Oh no, this is 90. Making mistakes. 15 onto 17,775 plus 15 is 1,7,790. That subtract from there is 2210, which is what this plus this should be, and this plus this should go here. Yeah, get it right. Sorry about that. All right, let's answer. Complete the table. What is the chance of someone testing positive? Okay, the people testing positive and not having cancer. So they tested positive. Well, there's 2,210 that tested positive and that not having cancer. That would be these 1975. And so I got to calculate that. So I got to take 1975 divided by 2210 times 100 to get a percentage. It's 89.3. I should only do that much. 89.3% chance of someone testing positive and not having cancer. Testing positive and not having cancer. This out of that. Okay. Two drugs, A and B, are tested on a total of 400 patients. 120 men, 280 women. Drug A was given to 200 patients. So this is given to 200 people. And there are 400, so drug B was given to 200. And the number of men was 120. And this was, which is 70 plus 50, 120. And women, there was 280, which is 130 and 150, 280 total number of women. So, find the percentage of cure rates for each of these. 42 out of the 70 were cured for men. So, I go 42 divided by 70 times 100, and I get 60% are cured by drug A. Let's see what percent of the women are cured. 46 divided by 130 times 100 would be 35.4%. Should only do a couple, but that's close enough. Drug B, 32 divided by 50, which is, I got an answer in there. Clear. 32 divided by 50. 64% cured. 54 divided by 150. 36% cured. Looks like drug B cures better for men and better for women. Give numerical evidence that drug A is better. Well, give numerical evidence that drug B is better. So here I can look at this one and this one. B is better for men and for women, according to the table. Give numerical evidence, and I should say men, which is 64 to 60. And for women, it's 36 to 35.4. Now, numerical evidence why A is better. Well, how many were cured by drug A? 42 plus 46 is 88. 88 out of 200, which is 44% overall. Drug B, 32 plus 54, that's 86 out of 200, which is 43%. So, overall, drug A was better than B. So you got to look at two things. Look at the overall rate and the split out rate on this one. And most of the time, there's often when they will not be matched evenly. And that's usually because there's a lot more people in one case than in the other case. Okay? All right, that's that sample test.